Right, we now have probably one of the top 5 most important definitions in the class. So what is a field extension? A field extension is, well, a field extension is a monomorphism, iota. I guess iota doesn't have the I, the dot. Iota from K to L, where K and L are fields. In our class, they're usually going to be subfields of C, but which is what the textbook has for this chapter. But in general, it's just a monomorphism of fields. We refer to K as the small field. Refer to K as the small field, and L as the large field. Sometimes I may say ambient as well, if it is appropriate. We will write, confusingly, L over K as a field extension, provided iota is clear. So the notation L over K doesn't really make sense because it doesn't remind you what the function is that related them. Yeah, so we'll often iota will be just the inclusion of a subset, which I will say here in a second, and so there's no confusion when you write L over K. And this is pronounced L over K. So K is the small one, L is the large one. Okay, so what are examples? Let's pick a bunch of examples. The best source of examples is subsets. So best and really only. Well, not true, but I mean it's mostly true, and only examples are subfields. And I'll say a little bit more what I mean by that. But whenever K is a subfield of L, there's a function it's called the inclusion homomorphism, and I'm going to call it maybe iota K to indicate you're including K into L. And it's an inclusion. All you do is you take an element of K and you just say, hey, I'm thinking about it as an element of L. K is a subset of L, so there's no problem there. And we'll see explicit examples of this in just one second. But since this is sort of naturally one-to-one, sometimes we'll put a hook here to really indicate it's like an inclusion function. So what is it defined as? If I give you a name of a function, I have to tell you what the rule is. It's defined by iota k of little k is k for all k and k. This is the best source of field extensions and really the only source up to me lying a little bit. Oftentimes when we're going to think about extensions, we're really just going to be thinking about, hey, I have one field and I have a larger field that contains it. That's it. That's really all we're going to think about. And let me make that clear with these explicit examples now. So there's iota 1 from Q to R, and then I can draw that little hook arrow there, where you take a rational number, P over Q, or I'm just going to write P, and you view it as a real number. So for example, iota 1 of 2/3 is 2/3. Every rational number is a real number. Is this a homomorphism? Well, if you is the one in Q the same as the one in R? Yeah, of course it is. Is is it true that if you were to add two rationals in Q versus adding them in R, do you get the same thing? Well, the addition's exactly the same. So yeah, of course you do. How could you get anything different? Is it true that if you were to multiply two rationals in Q and then view them as a real number versus view them as a real number and then multiply them, do you get the same answer? Well, yeah, of course you do. You have to. One is a subfield of the other. It's like that's the definition, right? Or that's the subfield test. All right, so there's that. You can view R as a subfield of C, where you have a real number and you make sure it's viewed as the real part of a complex number with no imaginary part. That's an extension. And iota 3, you can go Q all the way to C, where you take a rational number and you view it as the real part of an imaginary number. And notice here that iota 3 is really first view a rational number as a real number and then view that real number as a complex number. And in fact, that is true in general. Namely, if you have a composite of extensions, or it's really just a composite of monomorphisms, it is still a monomorphism. So there's a general fact in the background. I feel like we need a light blue for a cloud. Composite of monomorphisms is a monomorphism. And that means that the composite of field extensions is a field extension. Okay, so if I have one extension and then I have an extension extending that, I get a big extension. And we're going to study that quite a bit in this class. Okay, so those are silly examples, but there's also sort of the only examples, namely like when you have one as a subfield of the other. So let's do another example. I'll call this 2. In 2, we're going to let K, which I called, I'm just going to give it the name we use in chapter 1. We're going to let Q adjoin root 2 be the set of all P plus Q root 2, where P and Q are in Q. We saw that this was a field, or we saw that something similar to this was a field. The proof that this guy is a field is very similar to that. Q is a subfield of Q adjoin root 2. How is it a subfield of Q adjoin root 2? Well, you look at all P plus no root 2's. That's exactly a copy of Q. This tells us then that Q adjoin root 2 over Q is an extension. And here I haven't even mentioned the function because again, almost in all the situations we're going to care about, and in really all situations, the extension can be viewed as a subfield containment. And that's all that's happening here. We also had the Gaussian rationals earlier. So that's one example. Another example is Q adjoin I, which is of course P plus QI, P, Q, and Q. Q is a subfield of the Gaussian rationals, where we take P plus no i's, P and Q. So Q adjoin I over Q is an extension of Q. Furthermore, we had this Q adjoin, we had this field F in our motivating example of all P plus QI plus R root 2 plus SI root 2, where P, Q, R, and S are in Q. We didn't prove that it's a field. We will, but is a field. And this is to be proved, TBP. And what do you notice here? Well, there's the Gaussian rationals right here. And then there's this Q adjoin root 2 right there. So in fact, F over Q adjoin I, F over Q adjoin root 2, and there's also, I'm running out of colors here, there's also just P. And really, this is just a root negative 2. So there's also, let's see, orange. There's also a Q adjoin negative root 2 in there. Or sorry, root negative 2 in there. All of these are extensions that live inside of F. Extensions of various different fields, but they're all extensions inside of this field that we were looking at earlier. Wow, so cool. All right, so we're going to do one more example. So let's let Q adjoin root 2 be as before. And let's define, that is, P plus Q root 2, what we're looking at here. We're going to define a map, an interesting monomorphism that's not just inclusion. We're going to define iota from Q adjoin root 2 to C. This is a big extension. Namely, Q adjoin root 2 is countably infinite, C is uncountably infinite. So this is sort of a distinctly different type of example than number 4. We're going to define this by iota of P plus Q root 2 is P minus Q root 2. Okay. This is a monomorphism. Iota is a monomorphism. And I leave that to you to check. It's good practice. But it's not just include. It's sort of do a conjugation type operation on the root 2 part and then include. And that's fine. But is it really different than include? Well, yeah, as a function it's different, but is the image of iota different than just Q adjoin root 2 in C? And of course the answer is no. So notice here, let's just observe that the image of iota is a collection of all P minus Q root 2's, where P and Q are in Q. I'm going to let R be negative Q. Then as Q runs over all rationals, R is going to run over all rationals because negation is a bijection of the rationals. So this is the same as P plus R root 2, where P and R are in Q. Just a change of a dummy index, which is exactly sort of Q adjoin root 2 as a subset of C. So this is what I meant, like, yeah, it's not exactly that all extensions are monomorph or just are subset containments, but they're essentially that. Like the image of this guy is really just the same as you would get if you just included. Now this is again still not completely true, but in a lot of situations, these are what a lot of situations we're going to care about. These are the type of field extensions that are going to arise, whereas really just subset containment.